Okay, we can go ahead and start, but this is our presentation for our senior design on an RC aircraft. This is a group one presentation. Thank you guys so much for joining, and we can just go ahead and get right into introductions. And yes, this is recorded right now. So these are the team members. Aaron can start introductions.
Hello, I'm Aaron Merritt.
Hello, everyone. My name is Carl Wisniewski.
Hi.
I'm Frank Daldine.
Hi, I'm Jacob Cornell.
Next slide. I am Jacob Glenn.
Hey everyone, I'm Jared Seiler.
Hello, I'm Jonathan Abbey Dawood.
Hello, I am Juno Nelson.
And I'm Zachary Brown.
Okay, so just getting right into this presentation format real quick. We're going to go over the objective of this project and our derived requirements, constraints, criteria. Then we'll talk about our initial design, everything that went into that, the building testing process involved in that, and then some iterations that we did after our test flight, followed by a quick conclusion, some goals tracking. Going ahead right into the initial estimation. Next slide, please. Just to give an overview of the project objective, we wanted to build an RC aircraft that's only electrically powered, built from low-cost materials to have some sort of practical manufacturing as far as 3D printing to be able to quickly iterate and design a aircraft. The flight course is seen on your right here. It's about 2,000 feet per lap, minimum 3 laps in under 6 minutes. You need to have unassisted takeoff and landing. We've calculated speed to be a minimum of 30 miles per hour to get this objective done. We want the majority of this to be 3D printed. We're aiming for a target speed of around 40 miles per hour to get some sort of safety in there. We set an aggressive target weight of 4 pounds for a stable and easy to fly aircraft, and a target thrust to weight ratio about 0.5 to be minimum, which is pretty typical of an RC aircraft. Next slide, please. Zach. Yes, next slide. So going right into the initial design, we want to set up some baselines in order to get our plane running. Everything sort of runs off of the weight. And so essentially how we decide our baseline is we measured all of the OTS components, motors, batteries, control surface servos that we already had in lab, as well as looking at a previous plane that was PLA printed to try and get an estimation of what our weight would be. And we use that to get a target weight of about 4 pounds, which is a bit aggressive. We also calculated our speed to about 30 miles per hour. We are looking to have something slightly faster than that so we can finish with some sort of margin of safety. So we went about 40 miles per hour, 10 miles above the minimum speed limit without sacrificing too much speed and too much controllability. We also expected a wing loading of about 0.65 pounds per feet squared to 2.5, and that's a parameter that we got from the textbook that's very typical for RC aircraft. Next slide.
So jumping straight into our wing design, we used a combination of historical data for certain aspects of our design and comparison using some X-foil and also airfoil tools to figure out which design works best for our aircraft. We compared 3 airfoils after down selecting and focused on cambered airfoils, which would give us more lift at lower speeds and at an alpha of 0. We conducted a binary trade study comparing the coefficient of lift, coefficient of drag, thickness, range of alpha, and our stall behavior. We also chose the NACA 4412, which we'll talk about in 1 second, as it demonstrated the best performance among the other options, which I won't get into every single detail on the right, but this is a comprehensive overview of our wing, which our aspect ratio, our sweep, taper, incidence, twist, and dihedral all came from historical data and the text that we were given. The location was chosen to be a high wing for stability purposes, and our wingtip configuration was chosen based on manufacturability in our 3D print, as well as our CL over CD for the entire wing of 40.241 at steady level flight. Next slide, please. So jumping into the airfoil binary trade study, like I said, we compared seal over CD, the moment coefficient, thickness, alpha, and stall. Thickness was chosen based on packaging. The CM was based on the behavior of the plots. We tried to have as much quantitative inputs as possible. However, given the behavior changes throughout the range of alpha, we used a qualitative study for the CM and stall behavior. As you can see, that is the biggest difference for this binary trade study between the 4000 series and 2000 series, as well as the 4000 series. Ultimately, using analysis at Reynolds number of 100,000 and 200,000 for takeoff and steady level flight, respectively, we settled on the NACA 4412 as our final airfoil.
All right, so based on the wing parameters that we had established from historical data, one of the first criteria we decided to scrutinize was the wing stall, as well as the aileron performance. And the manner in which we did that was essentially we took the parameters of our wing that we had established, and we found that, and we aligned our wing loading values with the historical values for RC planes. We found that maximizing the root chord and wing surface area would essentially correlate to a lower stall speed for our wing. And so we optimized within the printing limitations that we had for our wing to minimize our stall speed, to improve our takeoff and steady level flight characteristics. Additionally, we performed analysis on the control surface size for the ailerons, essentially to maximize the bending moment, or apologies, the CM of our wing, and we chose the most responsive configuration, which correlated to a control surface across 20 to 90% of the wing, with a hinge located at approximately 87% of the chord length of our wing. Next slide, please. In designing the tail, we chose to pursue a conventional tail design, and we utilized symmetrical airfoils for the horizontal and vertical tail. These were relatively lightweight and easy to model, and additionally, the symmetric airfoils allowed us to ensure that there would be equal stabilizing forces on both the upper and lower skins of the airfoils themselves. As far as the tail positioning and size, conventional ratios for home-built aircraft were used to size the aspect ratio, taper, twists of the rudder and horizontal tail. And the control surfaces, specifically for the rudder, were sized primarily to pilot preference to give more sensitivity to rudder input.
Moving on to fuselage design, tapered cylindrical shape was chosen for our fuselage. This decreased the drag and weight with this shape that we chose. The diameter was chosen to be 4 inches. This was the smallest diameter that could accompany the motor and electrical system that we had chosen for the inside. And the length was determined by creating 2 different bounds, upper and lower bound, for what our length should be. Lower bound was created using this bottom right chart. This is the slenderness ratio chart, and it shows that the ideal slenderness ratio, about 5.25, would yield the least drag, and that gives us a length of 21 inches. And fuselage recommended length is to be about 75% of the wingspan based on conventional RC aircraft, and this would be a length of 32 inches. So we used the 32 inches as our bound and went with 29 inches to keep the end longer for a greater stabilizing moment arm when we added the tail, but still didn't go all the way to 32 to try not to veer too far away from the ideal slenderness ratio. Next slide, please.
So moving on to the landing gear, some of our main considerations were shock absorption on landing, overall weight, especially for an aircraft that's so light. Taxiing control, this became critically important as we got into testing. And then pitching control, being able to take off from the runway, from the pitching down moment from the tail, being able to pitch the nose up enough to reach the angle of attack to leave the runway. Looking at our conventional options, you can see 6 here on the right for landing gear configurations. We came to the 3-wheel tricycle design for a couple of reasons. Primarily, it performs well in the 4 categories I've already touched on, in addition to the fact that the crosswind landing stability of the pair of rear wheels behind the center of gravity provides a significant benefit for an aircraft that's this light. And we chose for materials the foam wheels and 2mm steel rods to support them for 2 primary reasons. One, the weight's exceptionally low, and the shock absorption is excellent as well, since you get some compliant movement out of the steel rods as you land. In addition to the fact that they can be modified easily and adjusted should you have any issues with either linearity of travel on the runway, or if there's any issues with an impact or a rough landing, they can be reconfigured within minutes.
So next was our stability analysis. A basic static stability estimation was carried out using the basic definitions of static stability. This is the partial derivative of each moment with respect to the aerodynamic angle being greater than or less than 0 for each moment axis determines stability. So these are seen in these 3 bullet points here at the top. L is the roll moment, M is the pitch moment, N is the yaw moment, alpha corresponds to angle of attack, and beta corresponds to the side slip angle. We only analyzed contributions from the wing, the horizontal tail, and the vertical tail. The fuselage was neglected just for simplicity's sake. And we used the cross product R cross F to find each moment in each axis. R was the vector from the center of gravity to the aerodynamic center of each component, and F was the vector of the aerodynamic force of each component at its aerodynamic center. And this cross product gives the moment in each axis. Each moment had its partial derivative taken with respect to its respective aerodynamic angle, and these are analyzed for stability to be either greater than or less than 0 according to those top 3 bullet points. And on the right here is a calculator we use to determine stability. Next slide, please. For trim, this was calculated as the sum of the moments in each axis is equal to 0. Each moment as a result of the stability analysis was calculated in the previous analysis. And now each force from each control surface necessary to counteract each moment and return it to 0 is calculated here. This was done using XFLR5 to create a table of data showing the resultant aerodynamic forces of each component, the wing, horizontal tail, and vertical tail, and using this to calculate what deflection angle of each control surface of those 3 components results in the needed force to trim the aircraft back to a moment of 0. And again, this is a calculator on the right that we use to perform this. Next slide, please.
Yeah, so I'll get into the propulsion system a little bit. So we first designed everything based around, again, recommended ratios based on historical data. So those 2 that we were looking at are the power to weight ratio and the thrust to weight ratio. We used our initial estimation values, and this table on the right, we found our power to weight ratio first, and then we used that to solve for our thrust or minimum thrust required using the thrust to weight ratio. And we used the total efficiency based on the propeller efficiency and the motor efficiency to account for losses that we would encounter there. So that came out to a minimum thrust required about 1.88 pounds, which is just under half of our weight. We opted into going for a single propeller design. This allowed us to nose mount our motor on our fuselage. And by having only 1 motor on our aircraft, as opposed to, for example, like 1 undermounted each wing, we're reducing the number of forces and thus not providing the opportunity for those forces to get unbalanced in some way and causing us to drift or something like that. The nose mounting did have a lower mounting position than on the high wings that we had discussed before. So we wanted to make sure that we're choosing a propeller diameter that wouldn't interfere with the ground during takeoff. So we calculated our max propeller diameter based on a KP ratio and our power of our motor. Came out to almost 20 inches. So we wouldn't run into any problems choosing a large propeller. So we noted the 4-inch diameter of the fuselage, and we chose a propeller pitch diameter that was greater than that diameter of the fuselage, just to have better air delivery over our aircraft. We did another decision matrix and binary trade study on the different motor options that we had searched up to select one. We were really looking at the percent throttle required to achieve thrust to weight ratio and the reliability. So reliability coming from just what motor sources can we find online that presented a lot of data and testing, and companies that were reputable. So we didn't want to end up purchasing arguably a very, very important part of our aircraft that would end up burning out or not work. So after that trade study was done, we came out to choosing this T-Motor AT2814. And when we went to go through the purchasing process, we ran into some supply chain issues. So we went with our next option, which is the Tempest 2820. And this Tempest motor is one that we had testing data on for different prop sizes from the design build fly team at UF. Getting into the electrical system a little bit, after we had a motor picked out, we knew that we needed a 4S LiPo battery operated on minimum 45 amps. So we went through and we looked at our power draw sources, the main two being the motor we're using for thrust, and then the servos we're using to deflect our control surfaces. So looking at the motor, we were saying, like, what kind of throttle percentage do we need for takeoff, and what kind of throttle percentage do we need for steady level flight? And then taking an average of those two to calculate the motor power draw, and then the servos, just looking at that middle chart there on the right to get our total power consumption. So then we compared a bunch of battery options to see which batteries would give us enough flight time, noting that we had to complete the course in under 6 minutes, but obviously wanted some room to wiggle there. So we ended up narrowing down onto this ZEEE3300 battery, which got us almost 11 minutes of flight time. The motor and battery allowed us to pick out an ESC. Basically here, we're just looking at which ones are compatible with our motor and battery, needed a minimum of 45 amps. And after looking at a few options, we ended up going with a 60 amp ESC, simply because it cost about half as much as the 45 amp one that we were able to find. This is a diagram of our electrical system, looking at just the different ways all the different components connect. The receiver and radio controller were given in the scope of the class. And based on the receiver that we had in our aircraft, we needed to make sure we picked out an ESC that had a battery eliminator circuit on it. That way we didn't fry that component.
Going into the structures part of the vehicle. So primarily we're looking at the wing here, which is what's taking up the majority of the load. But we assume the wing to act as a cantilever beam and bending. For our purpose of our calculations, we neglected the skin and ensured that the load would be going primarily through the spar. And the reason that is because the skin was relatively extremely thin compared to the actual spar itself. So the majority of the load would be going through the spar. It also allowed us to create a more conservative estimate for our factor of safety. We assumed about 40 miles per hour cruise at an angle tack stall angle of about 15 degrees, which would give us a worst case loading scenario. After that, we used some data from X-foil to get the bending moment derived from our expected wing geometry. Now, manipulating the bending equation, I was able to create what's called a C/I ratio, where it's just MC/I and it moves around a different way. You see the minimum C/I required to get a desired factor of safety about 1.5, which is pretty typical for aerospace design. Which is about 285 inches to -1/3. So designing the spar to meet those requirements actually ended up giving us a very crazy thin spar, which I didn't have a lot of faith in due to compliance issues. And since we had an 85% hollow requirement for mass, we had a ton of room to actually beat those spars up more. So the actual spars, we ended up upsizing a little bit, and we got a actual factor of safety about 4.3. As you can see in the picture below the MATLAB script, we have a wing that's printed in 3 sections. It's half the wing here with the spar going through the quarter cord. That allows to stiffen the wing as much as possible, as that's where the majority of the lift would act at, with the rib at the section ends The ribs are spaced out to allow us to maximize the wing size for our printing constraints while also stiffening the skins. And for these calculations, we also have to note that we adjusted the yield strength for a PLA based off of anisotropic properties. And we bonded the joints using 5-minute epoxy. Next slide.
This is a list of all components we use on the aircraft with their associated costs. Most of the off-the-shelf parts were chosen based on what was already purchased by the professor, but the control system parts were based on our trade studies and the type of controller we were using. Next slide, please.
So getting into actually manufacturing our completed design, the majority of our aircraft was created on a PLA that was additively manufactured. This allowed for not just easy prototyping and iterating through improved designs, but also it was extraordinarily lightweight relative to other materials that were available, especially because of the opportunity to completely remove the infill and make fully hollow or nearly hollow components. In addition to allowing for complex geometries, including hinges or mechanical interfaces between the components without complex manufacturing or having to include multiple components. Some of the constraints, however, with the additive manufacturing are the layer adhesion, particularly. So you have a highly anisotropic final component. In addition to the fact that this anisotropy has applications depending on not just how you orient the component, the final component in your completed assembly, but also how you orient it on the print bed can have significant implications for how strong the component is in any orientation. So if you look here on the right, for example, the component highlighted in blue versus the component highlighted in red have a 300% difference in strength in an average across all orientations. And so the both how you print and how you design for printing are critically important, and then orienting those parts properly on your final assembly. So then coming on to the next slide. So as far as actual assembly, wherever possible, we had mechanical interfaces between the components to ensure proper alignment and bear load where possible. And then in addition to this, the 5-minute epoxy, which as previously mentioned, had a higher shear strength even than our PLA itself, was used anywhere, both because of its reduced weight compared to metal fasteners, and also just because of its high strength and ease of application. And then moving on to fasteners, we had 3D print or heat set threaded inserts that melted directly into our printed components so that we could have easily assemble components that could be removable. For example, our nose cone to access the internal electronics, as you see here in the middle. And then push rods, so steel rods for components such as the control surfaces for actuating and interfacing with the servos, in addition to a couple hinges, some other components like you've seen the landing gear, and then secondary adhesives such as cyanoacrylate, just super glue, and hot glue as well for components where the adhesive was mostly to combat vibration and ensure proper location of the feature, but not highly load bearing.
Pre-flight testing allowed us to position the internal hardware to place the center of gravity at the quarter of our aircraft of the wing. We tested our control surfaces in lab to make sure that they had the proper amount of deflection and they moved in the right orientation. And yeah, next slide. Once we got to the field, we realized that there were some issues with taxiing, but we decided to attempt a flight anyways. And the result was too much elevator was applied during takeoff, which resulted in a really steep angle of attack on takeoff. And it stalled the plane directly after liftoff, causing us to pitch to, or roll yaw to the left. And we broke half the wing and the tail severed from the fuselage. Next slide, please. During our second round of pre-flight testing, we wanted to make sure our control surfaces were going to be able to respond with just the propeller wash moving air over them. So we tested that before we went out to the field, and we wanted to see, we did some taxiing attempts to make sure that we would have some rudder control while we were taxiing down runway. Next slide, please. For our second test flight, we had successful takeoff and we completed 2.5 laps. Due to visibility issues and a lack of a gyro stabilizer and also the amount of wind that was at the field that day, it resulted in the plane rolling in flight on the second half of the lap and crashing. So we lost the plane. Next slide, please.
Yeah, so going into the new goals of this project. So at this point, we are pivoting away from the initial design. At this point, we sort of achieved everything that we wanted on the engineering side, and just ended up failing due to a small pilot mistake. We were sort of unhappy with the conclusion of that, and we wanted to land. This time, we wanted to land a plane that we wanted to build without being constrained by cheap, brittle materials. So at that point, we decided to make a carbon aircraft for a couple of reasons. One is just to demonstrate our understanding of composite manufacturing. Two, just have a more durable plane and impact so that testing the flight is less risky, while also achieving a larger and more stable aircraft without having to gain too much weight. More importantly, we wanted to establish ourselves as a good group by setting an extremely aggressive redesign and rebuild goal and having to meet it within under 2 weeks. Next slide.
Yeah, so kind of going into the manufacturing of our aircraft, the carbon fiber, a carbon fiber layups that were used to strengthen the load-bearing components using 2-hour epoxy and vacuum bagging to increase our fiber volume fraction and therefore our stiffness. Again, this was done out of pure passion and not as much quantitative analysis, just kind of from experience, as a lot of us here have experience with this from our involvement in other organizations. And then we used hot wire, a CNC hot wire, to cut our foam to create the contours we wanted for our wings. And we use an extruded polystyrene, which in hindsight wasn't the best choice due to its compaction in the vacuum bag, but we were limited on resources as far as time goes and the supply chain issues of this day and age. But overall, we had higher quality foam for our tail components left over from other projects, which we utilized with great result. And we used 3D printed PLA for the fuselage components to strengthen them in the event of a hard landing or takeoff. Then we used 3D printed PLA for the motor mounts, servo mounts, tail connections, landing gear, and any connection between the wing and the fuselage. This was just for time, considering we had about 2 weeks to create an entirely new aircraft. We saved a lot of time doing this, and the results coming up.
Now, with all these different parts manufactured, we chose to use the epoxy and PLA inserts, once again, for the carbon fiber components, since in the previous iterations of the aircraft, these particular components held up very well. And similarly, we would end up using cyanoacrylate and hot glue anywhere else whenever a part is not particularly load-bearing. For any part that is load-bearing and still a PLA component, we would end up using epoxy due to its overall strength.
And regarding the third design, the size of the fuselage, landing gear geometry, and servo arrangement were maintained from the previous iterations. The main things that we changed were the size of the wings and the size of the tail. The size of the wings was increased by about 50% to increase roll stability and allow more lift at lower speeds. And then the size of the tail was increased by about 40% to increase yaw stability and provide more controllability. These changes led to an increase of weight of about 2/3 of a pound relative to the previous iteration of the aircraft. This is caused by PLA structural components that were left inside of the fuselage, and as well as tape that was used to smooth out deformed surfaces of the wing. The wings ended up becoming deformed because of lower quality foam that was used. Next slide, please.
Our third test flight was successful. We had a successful takeoff. More than any of the test flights we've done, we saw on this one that once we got up to the appropriate airspeed, our rudder engaged and we were able to taxi properly. Definitely due to the inclusion of a gyro and the increase in the size of some of the parts on the plane, there was much more stability with the rest of the aircraft during flight. Our landing was successful. The only damage we saw was slight debonding in the landing gear spars, but no damage to any major components of the plane. Next slide, please.
So overall, this semester was a great learning experience. We were able to successfully design and fly 2 planes, with the second one being completed within 2 weeks of the first iteration. The second one far surpassed the original course guidelines, and we were able to complete 5 laps and land under 6 minutes. If we were to attempt this again and have another iteration, we would look at adding a caster wheel for better taxiing, and then we would probably look to get higher quality materials so we would avoid deforming of stuff like the wing. Working with this group has been a fantastic experience, and that's going to bring us to the end of our presentation. Are there any questions?
Great job, everyone. So let's ask if our audience have any questions.
Yeah, I guess Tom Singer from Northrop Grumman. I noticed on slide 12 when you were looking at the slenderness ratio for fuselage.
Yeah, this is slide 12 here.
Yeah, there we go. Yeah, so the charts that you've got down there you've got curves for different velocities and velocities on the order of 200 to 240 knots, which is well above your airspeed, right? If you're flying at 40 miles an hour, so something like 35-ish knots, how does that affect where those curves are on the graph?
So we just used this as a we basically made an extrapolation to say that because at each of these velocities, it retained the same curve, even if the velocity was different. So we're not using the exact value of, say, non-dimensional drag on either side. We're just using the fact that for each velocity, the minimum appeared to still be about 5.25. So we just extrapolated that trend down to our velocity.
Okay. And then on, I think it was the next slide 13, when you were doing the trade study for the landing gear, and you're talking about the weight of your, I think the 3D print versus steel both came out to on the order of 4.5 grams or so, and then you've got like carbon fiber, looks like 57 grams. What drove the weight of the carbon fiber? That's very surprising to me.
So that
I could speak on that. So that was this was the carbon fiber was an OTS component that we found through hobby RC websites. The 3D print and steel rod was based on what we physically had in the lab. Like I said, the carbon fiber was what was advertised at that weight. It was because it was I guess intended for larger aircraft, so it was most likely reinforced at some point. But given
okay.
what was in the description for the product, that's what we had on hand.
All right, so significantly different form factor on that then.
Yeah.
Okay. On your structural analysis, when you're doing the idealization of the wing as a cantilevered beam, I really appreciate that you did that. I think that is 100% the right thing to do. I think what you found here is that sometimes manufacturing constraints are going to drive your design more so than structural constraints. Is that fair to say?
Certainly.
yes.
Yeah. Yeah, and that's often the case, especially when we're dealing with wings. And in my experience with wing skins. You've got constraints on how thin you can machine or chem mill down a wing skin, but structurally you need much less than that, and so that's exactly what you found in terms of sizing your spar. So I think that's kind of a good lesson to take away. I'll mention that when you're calculating a factor of safety, it looks like your load condition is just like a straight and level flight condition, which is probably not the highest loaded that you would expect this wing to be. I think probably if you were to like do it a little more carefully, you'd find that a landing condition is gonna be the highest load condition on your wing, especially the way that RC planes tend to land. So it might be better to take that as a loading condition to calculate a strength against. And then I've got a whole rant that I've been sending to everybody about factors of safety versus margin of safety, which I'll include in an email to you guys.
So the analysis using the plot you can see on the right and the X-foil output was done for the maximum angle of attack before stall at our maximum flight velocity, which still isn't landing, but just to give context as what you're seeing on the right.
Yeah, and that makes sense, and that's going to be probably your highest loaded straight and level condition, or maybe that's not even straight and level. Maybe you've got some upward acceleration there, but overall, if you're designing an aircraft, you're looking for what are the highest load cases for any given component, and so for a wing, it's going to tend to be especially when you're talking about aircraft that land with kind of a jolt, it's going to be kind of that impact loading.
Yeah, so just a couple thoughts on that.
In terms of the structural analysis, I think you were doing the right thing here.
Yeah, that was something that we were considering. Just some thoughts on that. The angle attack was taken at 15 degrees, which is about stall condition, so it's completely level. We did consider that the landing would probably be the highest loading scenario. However, that's going to be an impact scenario. So determining that for anisotropic material that's kind of glued together would be very difficult. So we instead to lean more so towards the testing side to validate if our wing would be strong there. And as we've seen from our actual crash flight, you can see that the actual wing kind of stayed in pieces. Or let's see. He's pulling up the picture now. That one right there. If you look at the wing itself, it actually stayed one piece. If anything, it just sort of sheared off. There is some failing in the actual plastic itself, but all the joints managed to stay together.
Yeah, and sometimes that kind of behavior is what you want, right? If you have a hard landing and you've got expensive components internally, if the outer structure can kind of absorb some of that impact damage, and you just go back to the 3D printer and print a new one, that can be a desirable way for an aircraft to fail like that. Well,
yeah, that was partially
maybe not aircraft, but for like an RC aircraft, that can be desirable.
Do you have any more questions, Tom?
I got a few more, but I'll take a pause.
This is Matt Trump. Can I ask some questions that are more philosophical?
Of course.
Okay. So I'm going to play devil's advocate here for a second. And before I do that, I want to, I think this is a great project, and I think you guys did a good job. And I think you're incredibly lucky to have Dr. Dong as your capstone advisor and mentor, because if you had me, you wouldn't have had nearly as exciting a project. But what I didn't hear anybody say is what's the point of all of this? Like, was the whole purpose of this thing just to build an RC airplane that was 3D printed or composite, or is there some fundamental underlying application? Are you guys starting an RC, a bespoke RC plane company? Are you guys contracting with the Army or the Air Force or some other military company, military agency to create aircraft in the field on the fly that meet specific parameters or requirements? What's the ultimate application of all this, or is it just education for the sake of education?
If you're asking for a prompt was not specifically part of the project objective. The project objective was merely to create an electrically powered, low-cost RC aircraft, to which we did achieve, and we did learn a lot about aircraft in that design aspect. Maybe in the future, the objective can be tailored to meet a specific industry, but mostly if you want to have an application for this, this is mostly pertaining to the hobbyist aircraft, which if you're looking at hobbyists, usually cheap materials like 3D printed, easy to assemble, easy to rapidly prototype is going to fit that bill.
Yeah, adding on to what Jacob said, I think that part of the kind of scope of the class is it being the first time that the class has been organized in this structure. So starting out with a baseline project objective like this, where there's no overarching or extra requirements in that way, allows to kind of get the head of the class under what's going on. And then as semesters progress, as we continue to learn, we can continue to add more objectives and more requirements into the scope of the class. And maybe then start talking about payload dropping or kind of other things that we can think about that would have either military applications or anything of that nature. But I think the proof of concept for building low swap RC aircraft that are easy to rapidly prototype and quick to manufacture is applicable to many different industries. But yeah.
Okay, so it's really so one element of it is education for the sake of education, which is fine, right? We're a university, that's what we do. But I'm hearing another aspect of it is you're basically proving capabilities, right? It's you guys are the first ones, I think, to 3D print an airplane, at least with the resources available at UF, and I think the first capstone group, at least that I'm aware of, to use all the composite stuff for an airplane.
Yeah,
that's correct. Yeah,
that was part of the motivation for building the carbon plane as well, is just to prove that it could be done. Most students throughout university don't have a lot of experience with composite manufacturing, so we want to show that if you put your heart to it, you can easily do it.
Yeah. Okay. So in the parlance of Mech 2, you guys are basically advancing the technology readiness level of small scale bespoke RC airplanes.
Yes.
Yeah, gotcha. Okay, no, that's fair. So that was my first question. My second question is, and well, I'll just ask it. I think I know the answer. It might just be resources, but you showed this video of your initial airplane, taking off and swerving to the side and crashing, which set up a really nice story for, we wanted to, be the phoenix that raised itself from the ashes. And that was, yeah, there you go. Did you guys do any wind tunnel testing, any experimental testing on any of this stuff, or you just trusted the theory in the textbooks up until the point where that happened and then realized that, oops, we need to do something different than what the textbook said?
So we did not tunnel test the entire aircraft. The problems that we saw here are not related to the aerodynamics of the aircraft. They were deduced to be a problem due to controller input and also the location of our center of mass in the aircraft, which was correct in the textbook. We were very close to our ideal location, but due to the constraints of time where we were testing and the resources available, we just wanted to see what would happen. And that's what we saw here. It was less of a problem in aerodynamics and more of a problem in statics. But our input with X-Foil, a couple of us here are taking Aerolab at the same time right now. and we had to compare X-foil outputs to our wind tunnel testing, and they align fairly close with the correct inputs. So in the context of this course, we simply use XFOR5 and the X-foil program to do this. But yeah.
Yeah, if I could speak of the pilot, just to echo what Carl said, he's absolutely right. I was not used to flying heavier aircraft. Most of the RC aircraft I've flown have taken off within 2 feet. So having a heavier aircraft definitely was pilot inexperience. But between this flight and the second test flight, I was on the simulator training and trying to get aircraft that more resembled what we were using versus that. But it's exactly what Carl said.
I noticed in that that first test flight, you started way over to the right side of the of your runway. Was there a reason for that? Were you expecting it to kind of be trimmed to go left?
Yes, we were having taxiing issues. We were attempting taxiing attempts, and the aircraft kept yawing to the left, even when we would apply rudder. But because we weren't at a high enough airspeed, the rudder wouldn't engage. We wouldn't really be able to steer the aircraft too much. I think also the trike design on the aircraft landing gear also didn't assist too much. And we revamped our landing gear design, but due to the way that it was constructed the first time, there was slight deformities in the positioning of the wheels, and those slight deformities took over anything that the rudder could really do.
Yeah, if you go back to the slide where we have the initial landing gear design, I think it's up in the manufacturing section. Or the landing gear page, maybe.
Slide 13, I think.
13, okay. Yeah, you can kind of see here how we have on those front wheels, those 2 larger wheels, we just have steel rods coming down and they're bent out. And the manual bending of those rods created some angles in the wheels that we were sitting at the flight field as we were doing taxiing tests, trying to bend them back and forth to get them as straight as possible. And it wasn't really working. And so as we go into our landing gear redesign, you can see what we ended up doing is we switched to a system where we had straight cut steel rods, and then we used 3D printed parts with locating features. That way none of our rods were bending, and we were relying solely on the geometry we developed in CAD in order to keep our wheels straight. And this helped enormous amounts in keeping our taxiing straight as we moved into that second test flight.
Yeah, it seemed.
Go ahead.
The wheel system seems like it's going to be like, I don't know, really prone to small errors, and that I think that caster wheel is probably a big help in that regard, right? So you don't have that friction kind of working against your rudder inputs.
Yeah, yes. And that was something we mentioned at the end of the presentation. If we were to complete another iteration, then we would for sure add a caster wheel, because making that taxiing easier would be very nice.
One of the other things that we did in between that first test flight where we got left and crashed, and that second one where we were able to at least get off the ground and do a couple laps, was our motor configuration. We added washers between our motor mount and the motor interface itself to cant the motor to the right. And this helped to, it was a suggestion by one of the people that was actually at the RC flight field when they saw our plane crash the first time and we were doing our taxiing tests. They suggested putting some washers in there to help counteract the torque of the motor and that yaw moment it was creating. And after we made that change, we kind of kept playing around with the number of washers that we added in there and kept doing taxiing tests, and it helped to significantly improve our ability to taxi on the runway.
Okay, any other question from our audience?
I was kind of curious, when you did the carbon fiber version of the plane, did you do anything to like tailor your layup, or did you just sort of stick with like a single ply 090 fabric, or what did that actually look like in practice?
So we used a 3K plus minus 45 oriented, I guess, oppositely. So in a way, yes, but we kind of just, because everything was so expensive, and this was honestly just a way for us to showcase our ability to use carbon fiber. We kind of just cut the fabric out as we could with the amount that we had. But we used the 3K plus minus 45 for everything.
There's also a bit of a time constraint as well. So getting it to be like really nice carbon fiber work is gonna be difficult in our time constraint.
It would have been nice to do some laminate code there for some unidirectional things like that. But since we only had 2 weeks to do this, we kind of just put it together to have it done. I mean, it still didn't fail. It would have been nice to have some sort of quantitative analysis on our layup schedule, but that was not the case just with the time constraint.
I guess sort of to put it succinctly, we were kind of relying on the strength of the material. The loading condition, as we mentioned, the PLA itself was fairly anisotropic. So we're mainly relying upon the strength of the carbon fiber laminate itself to reinforce the plane, rather than sort of tailoring the layup schedule to fit our load case.
Did you have a rib and spar construction, or was it just the carbon fiber skin over like a full foam core?
The latter.
Okay. It's also significantly stiffer than the PLA.
Oh yeah.
Any other question?
Yeah, am I allowed to ask one more?
Yeah, of course.
Yeah, so I asked you guys this already, just in passing during the class, but now we can get it on the official recording. So, as you guys know, I teach is the wrong word. I lead summer camps for high school kids who are excited about STEM, and how do we get this capability of being able to design and 3D print and assemble and fly an RC airplane into the hands of high school students in STEM camps?
I'll take this at least for a first shot. So I'd say the biggest thing we need to look at is modularization, which was already something we worked with in some capacity just based off of our size constraints from the 3D printer. So a lot of our components were designed to be printed in sections and combined. And so starting with this and improving the interfacing between the components, you can build something where you're taking what you've created is basically an off-the-shelf component where you can vary your fuselage length or vary your wing length or vary your chord length, but with just connectable components, or taking the most complex components and having basically an outline so that you simplify the most difficult manufacturing and turn it into a lesson on how the aircraft actually works. And so that the decision making for these high schoolers trying to learn these things and trying to assemble an aircraft is about how the aircraft flies and not how to make a hinge straight.
Yeah, I would agree with Cotton, and I would even go to say that probably a great starting place is just teaching them how to fly RC airplane. I mean, there's a lot of starter models. I think before you can even touch manufacturing, you have to know how the plane works, what you're looking for, how to make it more stable. I think just putting one together wouldn't be as beneficial as knowing how it works before you do that.
As far as kind of developing that camp goes, I'd say that a good thing to do is maybe just create a bunch of different models, and probably a lot smaller scale would be more palatable to what we're doing. But just a bunch of different models, different airfoil shapes, wing sizes, stuff like that, and maybe 1 or 2 different modular fuselage designs. That way you can use the same electrical components within it without having to modify that geometry. And then just having different ways to either do snap fits or again, just keep using epoxy or something like that, but then have all of these different tail designs, horizontal tail designs, wing designs and whatnot. And then just having the people attending the camp, these kids, like come in and then do a general basic lesson on kind of what the different geometries do to an airplane, how that works, and then going in and just having them make those decisions. So a lot of the complicated CAD work of creating those surfaces wouldn't be on the students, but more so in making those design decisions and then being able to quickly print it out on a small scale, put it together, and see if we can fly.
All right. how small can this thing get? I remember walking into the lab and seeing these like, huge wing sections sort of growing vertically off of the 3D printer, and wondering if they were going to, break because they were so big and tall and monolithic and thin walled. But if we were to do it at a smaller scale, how small can you go before like you just can't fly it anymore because it's too small?
There's a concern with I think there's two things that you would be concerned about. The first thing, whoever moved the slide, thank you. You need to create like the flow. If your Reynolds number is too low, it becomes basically unpredictable. Unless you increase your velocity really high, that won't be the case. Additionally, you're constrained by your motor size and your battery size. So if you can find motors and batteries that work together that are small enough, then you could probably do it. The only problem is you're gonna have to have really, really small hands or tweezers to put everything together inside if you're doing like a servo thing. Because even the small one, I know Jarrett was flying it to practice, but that thing is made like out of foam. It's just like made out of one piece. It's super light. But when you're trying to do something where like it's all custom components, it's way too complicated wiring wise. Because additionally, we had a gyro. I don't know if it was highlighted in large detail, but we had a gyro that really helped us out. And that itself probably won't fit in a tiny aircraft unless you can find a really small one. So it's a basis of integration, and that kind of sets your size, because then that sets your weight, and that weight sets your wing size. So it's kind of like a cascade.
Yeah, I would also be worried about the controllability of the aircraft itself. If a lot of these students are high schoolers with little experience flying, having such a small aircraft that could be so lightweight, I mean, it could respond very extremely under any perturbations. And that's just not ideal for something that could crash very easily and explode. I would say if you really want to downsize it, you can change the scope of the project to be like a drone as opposed to a plane itself.
Yeah, we've actually had that discussion, and we're not sure, at least I'm not sure at the moment, about the future of drones. There's been some federal regulation that has kind of limited what universities can do. So that's why I'm asking about fixed wing airplanes, because there's a ton of regulation, but there isn't like a law that says if you 3D print your own airplane, you can't fly it. And it seems like, at least based on some of the conversations that I've had, that the government is moving in that direction with respect to drones. Is you can only buy them and fly them if they come from specific manufacturers. So it seemed like this was a nice alternative. But yeah, I had an RC plane once when I was a kid, and it lasted all of 15 minutes. And I crashed it, and I didn't, have the knowledge or the resources to fix it. And that was sort of the end of my RC plane hobby, because it was like I spent my entire like year's allowance to buy it, and it was toast in 15 minutes. So anyway, yeah, giving high school students an RC airplane that takes them, weeks to manufacture, and then like, the video that you guys showed basically takes off and veers to the left and smashes on the runway, I think would drive them away from engineering, maybe, rather than towards it. So we got to think a little bit more about how to do that. But anyway, okay, I'm good. Thank you.
Just real quickly to sort of cut in on this. Another factor to consider in this is we had a time limit for our flight that we needed to operate within. So that drove a lot of the decisions in terms of like our wing geometry, our speeds that we operated at. I think it would be possible to scale it down as long as you're careful with like the Reynolds number of all the aerodynamic surfaces for controllability and predictability. So essentially, I think it could be scaled down. I think you just need like a fairly like lenient requirement in terms of like course layout, speed, and so on and so forth. Like something like a glider would probably be ideal to have them start out, something that you can operate at like a low speed.
Yeah, exactly. I agree.
Yeah.
I think just from when we were testing, there was a guy came in with a massive like glider, really thin wings, basically just sections that he like put the tubes in to like connect them. The thing was like 10 feet wide and it flew like 10 miles an hour and landed very softly. There was like minimal components. I think he had a tiny little motor just to get him up and he just glided it. Something like that where it's a little bit bigger might be a little bit easier to control and then most likely less chance of crashing and smashing to a million pieces. But there's like different ways to go about it, but it's definitely possible. It's probably going to take some time.
All right, thank you.
Any other question from our audience? Okay, so overall, great job. And I have some comments on your presentation. So start from the very beginning, page 5. So I see that, okay, based on the our project requirement, you have the initial estimation, like the speed and everything, and the thrust weight ratio. What is the wing loading estimation? Because on page 7,
yeah, let me pull that up real quickly.
You have a range of 0.625 to 2.5, but that is like a very wide range for all RC aircraft. But what is your target based on our requirement?
Mm-hmm. So our target was to essentially lie within that range that was typical for RC aircraft, and the target was essentially to try and minimize the wing loading factor as much as possible. Yeah. Again, since that would decrease the takeoff speed and the stall speed in general of our aircraft. So our target was essentially to lie within that historical range and drop it, be as close to the lower bounds of it as possible.
Okay, so when you put it like from 0.625 to 2.5, your target is 0.625.
Yes, but we were limited in what we could achieve through the printing limitations that we had for our wing.
Sure. And another thing is that on page 9, so you have a trade study of the airfoil, and I understand that like lift drag ratio and moment coefficient behavior of a range and stall behavior, we know that, okay, we know how to quantify them. But the thickness ratio, I see that you do in a way, the higher the thickness ratio, the higher score. I mean, why? Why the highest thickness ratio it's better?
So yeah, I can talk about that. It's not readily apparent. I just, for the sake of time, we wanted to finish, so I didn't explain every single aspect. But when we had so we were at this point in our design phase, when we were just picking an airfoil, we were concerned about packaging limitations because we wanted to include our servos inside of our wing. And at that point, we were still kind of figuring out how everything was going to come together. So we wanted a thicker airfoil, and that's why it's not weighted very high. It's only 7.5. It's not weighted very high because we were concerned that if we chose too thin of an airfoil, that we wouldn't be able to package everything the way we wanted to.
Okay.
So that's why we chose a high. The difference is very minimal there. If you look at the magnitudes, but it didn't change obviously here you can see it didn't really change that much in it. It was just what we came up with for that.
Yeah, I understand. And so it is because you the packaging everything. And also I think I'm not sure I'm correct, but I think there is a curve, like, okay, for thickness ratio of the aerodynamic performance, there's a curve. It may like increase and then decrease. So there's an optimized thickness ratio. And I feel like if you can combine your own reason with that curve, that'll be like, it's not the higher the better. I think it will optimize at some point and then it will decrease. So
yeah, I definitely agree with you. I mean, it's also exhibited in the data below. We chose that based on packaging. It was nothing else, but the other things that we can see as the other categories for like the parameters that we use in our trade study compensate for that difference that you're talking about finding an optimum. So that's why you're seeing the CL versus alpha and the stall behavior and CM. You can see on the second plot and the second to last plot, you can see that at the lower Reynolds numbers, the 4412 actually stalls a lot smoother than the 4415, which is likely due to based on the Reynolds number and the thickness ratio, because that's the only difference between the two. So as a pros cons, we weighted them in that context where we cared more about the aerodynamic performance, and in order to include other aspects, we included the thickness ratio to compensate the weighing to figure out whether or not the aerodynamic performance or the packaging is more important, and that's what we can see here.
Okay.
I think is what you were getting at. It's,
okay. Another question is that, another comment is that one is orange line, one is yellow line. Can you tell the difference from the graph?
Yes. So the problem is we use airfoil tools.
What I mean that it's okay. Yeah. I mean that when you make the graph,
the one that you could see stalling sooner, that is the 24.
What I mean that when you make a graph like this, make strong contrast color.
We couldn't choose that sadly in the website, and we're trying to get that to work. But I see your point. You're
yeah,
because
it's you really want to use some strong contrast color, so when people see it, they know which line, which airfoil they are reading.
Yeah, I agree.
And also one like general comment for your slides is that some slides they are just too busy. Is one slide have too much information crowded in one slide, and that's kind of like it's really hard to follow if you have too much information on one slide, and it's really hard to read. So I would rather that split into several slides. There's no limitation like how many slides you should use, but we want to make our presentation as clear as possible. So for the busy slide like this, just split it into several slides. It would be much better.
Yeah, the reason why we included it here is because it would be difficult to remember numbers from a previous slide to then correlate them with the table. So this was kind of seeing everything cohesively on one page that we could figure out. We could easily see why you can see the behaviors in the table with the plots below.
Okay.
But thank you.
Then probably you can put like, okay, the lift drag ratio and put it as one slide. You can have the value, have the table, you have the graph, and then put the moment coefficient behavior on the other side. It's always making it, well, I personally don't prefer to have too much information on one slide. If you can find some way to split into different slides, it will be much easier for you to explain. It's much easier for audience to follow. That's what I mean.
Yep, I understand.
And also on the next slide, 10, page 10. Iterate to maximize the moment coefficient of the wing. Why that?
The reasoning for that is we were kind of concerned with reaching a spiral mode that we needed to correct with our ailerons. So there's an interplay between the performance of a control surface and the control you have over it through your receiver. And we decided that having a higher moment coefficient was ideal because that would give us a higher range of corrective roll from our aileron. Which we could trim in the receiver if we found it was too much.
Okay.
So having a high, we essentially wanted a high upper limit in case we did catch like a spiral mode to correct ourselves.
Okay. In the table, again, this is too tiny. Approximate takeoff velocity, miles per hour, and there are like negative 30%, negative 26%, negative 23%. What is that?
So those are the deltas of the various iterations that we ran through XLFR5 versus a baseline with no aileron. So just a fixed wing, no control surface actuation. So that's essentially comparing based off the effect on. So to give some context to this, we were considering a flaperon design for our aileron control surface to increase, or rather decrease, the takeoff velocity by increasing our maximum achievable lift with our wing. We didn't implement that design. I think that column was just left in by mistake primarily.
Okay. And also for slides like this, just split into different slides. And page 13. I think the consideration landing gear design, the consideration put here, shock absorption, weight, taxing control, pitching control. And when you do the trade study, it is the weight, manufacturing time, cost, and ease of modification. So I feel like, well, if you have the consideration, you already list all the considerations, but when you do trade study, you didn't put the consideration in your trade study.
Professor, can we pause for a second? I just wanted to thank Northrop so much for your time. Thank you for coming. I know you guys have to go, but yeah, thank you so much for giving us feedback and listening to our presentation. We really appreciate it.
Could you repeat the question?
Yeah, I mean, you have 4 consideration there, but in your trade study, you didn't use the 4 consideration. I mean, you want to consider the shock absorption, but when you compare the 3D printing steel rod and carbon fiber, you didn't compare their shock absorption capability.
So the landing gear considerations that we're doing are for choosing our landing gear design overall, like just the form factor of our landing gear. And then the trade study that you see is the 3 different material choices that we can use to implement that form factor. So it's kind of 2 different concepts, right? Like the considerations is what do we care about in our landing gear? And then in the landing gear trade study, we're looking at, okay, what are the different material choices that we can? And yes, maybe shock absorption should have been one of those, but we did not include it.
And for the stability, next slide, 14, page 14. So for the range of the derivatives, I think we should have a narrow range we should target. It's not just, okay, if it's some derivatives is negative or positive, your stability is okay. I think the range should be much narrow than just say positive or negative is fine.
Why would it need to be narrow? I'm just curious.
You want to have a better target.
Yeah,
I think what we were trying to convey was just that this was the condition required for theoretical static stability in the wing. This wasn't necessarily this was just the target that we had to achieve to have some form of static stability.
Mm-hmm. I can see what you mean, if like not, because too stable means, you know, you can't turn, you can't maneuver and stuff. I think we just made for the assumption of this aircraft, since typically the trade-off between stability and maneuverability is something to consider when creating something like fighter jets or something that needs to be very maneuverable. For RC aircraft, we kind of just left the open bound of the more stable, the better, because there's not really a chance we're going to, and in my mind, there's not really a chance we're going to end up making it too stable. But I can see that I didn't really explain that part here. And that makes sense.
Yeah. So on page 16.
Mm-hmm.
So Maybe it's because you calculation here, you use the velocity feet per second, but I think for the whole report, when you do the final report, I hope it's better to make the unit consistent. So you have the mile power at the very beginning, and in your graph, you have the knots, and now you have feet per second. It's better to make it consistent of the unit. Otherwise, people will get confused.
So just using feet per second here, because that's how we cancel the units in that equation, the second bullet point under the thrust to weight ratio.
I mean, when you talk about speed, when you want to use mile power for the whole report, use mile power. If you want to use feet per second, that's okay. Use feet per second for the whole report, but don't mix all the units. And
okay.
And on page 18 and 19, I feel like majority of trade study did very well, but this trade study on these two slides, the trade study is like, I don't see a very clear logic in it, like why we choose a specific one and which one did you choose and everything. So you just list everything, but it's not very clear to the audience, like how your decision is made.
Yeah, that's correct. So what you're seeing here is not a trade study. We're simply kind of defining what our limitations are, right? And then going through finding a bunch of different battery choices and looking at, okay, which ones satisfy our requirements, and then looking at, okay, so weight and battery cost are two parameters that we might care about, right? Which ones have the lower weight, which ones have the lower cost. They all have a satisfactory voltage, so that's okay, because we wouldn't pick a battery for one of those choices if it didn't have the correct voltage. And then we're looking at the estimated flight time, and that's in the factor margin of safety there. And those are two calculated values. And so we're looking at, okay, the green ones are the ones that show the best performance, and then the estimated flight time for the first one being a little bit less and the last two being worse than that. But all of them meet the minimum requirements that we need to fly 6 minutes. We're just comparing different battery options and saying, okay, this one is going to be the best here. We could have done a trade study based on that, but given that they all met the minimum requirements that we needed, we just selected one.
No, I understand. So I think it's better you just show what the green means, red means, and yellow means.
Yeah, we have that detailed in our report. We just didn't include it here in this slide in this PowerPoint presentation.
I think that information is very easy. You just put like green, yellow, and because if I didn't read your report and I just read this slide directly, it's hard for me to tell, okay, what is green means, what yellow means, and what red means. So for me, it doesn't show very clearly what is your decision making and what is the conclusion.
All right, understand.
And for the structure analysis, page 21. So you show the C of I ratio, you show the yield strength of the material and safety factor, but the whole purpose of structure analysis is design. And I want to see your conclusion, like what is, using this as a guidance, what is your actual design? So if you say, okay, the wing spar carries a majority of load, okay, what is size of the wing spar that satisfy our structure requirements?
Yeah, so I didn't include the exact wing spar, but I just sort of glossed over it. But essentially, to meet that minimum requirement, it was like paper thin, and at that point, it's like completely compliant.
But I think it'd be better to show, well, when there's a limited time and limited space, always think about like what is the most important information to show. So I would say that, okay, for structure design, what is the final design? What is the dimension of the spar? And what is the stress, maximum stress in your structure? And then you can compare, okay, yield strength, PA is given here, the epoxy is given here. And now I can say, okay, the maximum stress that in your structure is what value, and the yield strength is what value, and I can see how safe your aircraft is.
Yeah, part of the point that was driven across in this particular slide, and I think Tom hit on it pretty well, is that on the structure side, we tend to be actually very overbuilt, regardless of how little we tried to get, and that more constraints were more so on the manufacturing side, which we demonstrate later in the presentation. Like we could provide like more details, but at that point, I think it'd be sort of nitpicky. to try and elaborate on that when we're missing the main point is that we're manufacturing constrained, not structures constrained.
Let me see. I think that's all the comments I have. Overall, great job for the whole semester and a great job in the final presentation.